Okay, hey everyone. Our next speaker is Zach Lipton, now assistant prof at Carnegie Mellon. Zach has done work on a whole bunch of different things and won various awards. The things that my students have been looking at is he's been trying to figure out sort of what many things that can go wrong in these things and how to sort of fix them. So.
Cool. Thanks for having me. I imagine the shades are down to keep out the sun. Gotta get your vitamin D. So I think every time I have a set of things I want to cover in this talk, and every time I try to give it, I don't get to them all. So this is possible that we might, if we're really fast, get over them. So I'll describe work in a few different papers. This is an opportunity to accelerate. My work is with a bunch of great collaborators. We have a really good pace so far, so I'm optimistic. Okay, so here's the high-level kind of frustration. Is we have in machine learning a set of machinery that we are using to build technology and throw at all kinds of problems, and it's based on this kind of very delicate view of the world. And it goes like this. God showers data out of the sky. We harvest. I'm sorry God's a man here. I was looking for a photo from antiquity. They were kind of backwards back then. I'll find a more modern, female God for the next version of this talk. We harvest a subset of the data. We use it as the input to a machine learning model or a machine learning algorithm whose output is a model, and we evaluate it by just taking a random partition of that data. So basically we're kind of explicitly making this assumption that this is what deployment looks like. Deployment is might as well be like a random partition of the data that came out at data harvesting time. This the IID assumption that's like the backbone behind all the technology that we build. And the idea is that if this is true, then the test set performance is a good approximation of the true risk, and we should expect that our classifier is going to do great, or our model is going to perform well in the world. And that's just not what happens. What happens is somehow the future is different from the past. It's always different from the past. Wednesday is always different from Tuesday, and year T is always different from year T minus 1. And so the question is, this sort of fundamentally violates the assumptions that underlie the validity of sort of all of the technology that we're building. And it's like, what in general, or what under what set of assumptions can we still sort of proceed? So, I think we could sort of start thinking about. Maybe the more general agenda here is sort of like, beyond the train test paradigm, or beyond just like the most naive form of it, and I think we could start coming up against this sort of beyond supervised learning as usual from a number of perspectives. I mean, there's sort of consideration of from a standpoint of robustness, like you say, even if our distributions are almost the same up to some perturbations and there's some adversarial actor trying to break our technology, we know that it's brittle. This is something that we don't get for free from just sort of standard train test training, and the sort of burgeoning literature on adversarial examples shows that even if we are just impossibly restrictive about the set of threat models we consider, we still are having trouble producing models that are robust. This isn't just true for images. So with one of my, I guess now my PhD student, at the time just an ally, Danish Pruthi and Boan Dingra, who's on the job market, by the way. See what a good friend I am. We showed that basically you take state-of-the-art sort of document classification models for, say, in this case, sentiment analysis, and you attack by the most restricted set of attacks. We basically say you're allowed to change one character. It's one character in the document. And we're even more restrictive because there was some kind of meme psychology study at some point a long time ago that then got packaged as a popular blog post by Cambridge Linguistics, where they show that like if you completely scramble the text in a document, preserving the first and last, so you keep the same characters, but you scramble them, keeping the first and last character of each word, and humans could just read the document and get more or less the same meaning out of it. So we say you can attack one character, you can't attack the first or last character in the word, and you can only attack words of, say, like length, I forget, I think it was 4 or greater or 5 or greater. And still, a single character attack is enough to bring down the performance of models from 90% to 45%. I won't tell you just how devastating a two-character attack can be, but you can use your imagination. And this is true even when we confine the nature of the character attack to say you can just drop a character, or you could just swap to adjacent characters, or you can add a character. Interestingly, here in this study, you might think that a character level model might be more robust. You might think, well, because it could pick up on, if you attack a word level model and you flip a character, you made it a completely different token. If you attack a character level model, a lot of the morphology of the word is preserved, so you might think that model is going to be more robust. But actually, the character level models are more vulnerable. And part of the reason is that for a typical word, you sort of have a choice to keep the original word or flip a character, which is going to turn it to unk. So you have 2 choices for how that word presents to the downstream classifier. For a character level model, it sees every different combination of characters as a different input. So in a sense, you actually have more surface area to attack. So that's not the main subject of this talk, but we have a lot of cases where we construct tasks in a kind of programmatic way or in simulation, and then we hope that they're representative of some kind of underlying competence or capability, and this doesn't always work out. So this is my student Divyansh got this Best Short Paper Award at EMNLP for a paper that we should not have been able to write, which basically showed that a lot of people are interested in tasks with question answering, and we're building models where the high-level idea here is you say we have a passage and we have a question, and the output is an answer. Right, so you input a passage and a question, the output's an answer, and people propose all kinds of complicated deep learning models where they tell a story about how the model is jointly attending to the question and the passage. Presumably, the model is reading the question and reading the passage, and that somehow both the passage and the question are taken into account and deciding what the answer is. But it turns out that a lot of these models but what you're really hoping you're going to do is not that it's going to perform well. So these tasks are often constructed in a way where they'll do something like take a CNN article, grab out accompanying bullet point. They'll drop an entity from the bullet point, and then they'll say the blanked out bullet point, the masked bullet point is the question, the dropped entity is the answer, and the passage is the passage. They've created these data sets in interesting ways, which it's not quite clear if this is actually something that can representative of how you might try to deploy the model or the types of questions you might get. And what we found is that actually if you took these same models and you replaced the questions with random words, you can often get the same performance that was achieved in these papers and claimed as representative of representing that they in fact had this sort of question answering capability. And for some other tasks you could drop the passage and just look at the question and you know what the answer is. There's a lot of things we should be worried about. I think oftentimes just future data looks different from past data because of, sort of not necessarily because of the model itself, but just because the world's changing, cameras get different. But sometimes something more insidious happens, we are engaging in systems where we're fitting models based on historical data. We're not taking seriously the task of how you create a coherent policy or how you should drive decisions. The decision-making part is sort of punted on or just accomplished sort of thoughtlessly with some ad hoc heuristic that we just sort of check, short-term business performance in A/B testing. We deploy some kind of technology into the world where actually, the deployment of the technology itself undermines its own validity. We are ourselves the agent that make our models not make sense. So in the case of recommender systems, you harvest a bunch of data on what people click on given what they were previously shown, and you use this to show them something different than what they were previously shown, and now you've put yourself out of support, and who knows in this new world that we've created what people will click on. So even the things become coherent even with respect to the prediction task, let alone like from a business standpoint. So you might think like, okay, let's just, when you're worried about distribution, so now let's talk about distribution shift, just focusing on, classification. You might think, well, let's just come up with, one robust classifier that'll, and you see a lot of claims now where people are doing something. We've got an adversary here, we got something there. There's an extra layer, and the layers talk to the other layers, the skip connections. Like now it's robust, and there's this kind of like storytelling that happens where sometimes people sort of say, "Oh, we have a model; it's robust to distribution shift. Like, why don't we just produce that model?" It's actually impossible. So, given the same, and I think that this might be like slightly surprising if we've only done supervised learning. If there's anyone here who does causal inference, this might be quite obvious. You say, hey, there's lots of problems where depending on what assumption you make, even given the same observational data and even given the same an infinite amount of it, what you're after just might not be identifiable from observational data alone, right? So if a good example of this is, I don't know. You have an infinite amount of data, x and y. And x and y are the only, two variables. Nor say what's the causal effect of x on y. It doesn't matter how much data you have, And basically, what you're asking is you're actually asking a question about distribution shift. You're saying in a mutated world, in a world in which I intervene on x, now what would be the conditional probability of y given x? And that's there are different sort of structural assumptions that are both compatible. Like anyone did probabilistic graphical models, that the two variable world in which x there's an arrow from x to y, and the two variable world in which there's an arrow from y to x are both compatible with any joint distribution over x and y. You specified a no conditional independency. So anyway, I'll pop back up the stack and we'll talk about distribution shift. So in general, it's impossible absent some kind of further assumption. No classifier will work well on all distributions. We can guarantee performance under some strong assumption. I'll kind of make an argument here that even when those assumptions are a little too strong and will never be realized, there's often like a value to backing out and establishing some kind of machinery under coherent assumptions and then going back to the real world and trying to figure out what we can do with it. Typical assumptions are some kind of bounded divergence between source and target distributions. We'll use these when we talk about distribution shift. I often just talk about like a two epoch world in which there's the world in which we harvested our data and then the world that our test data comes from. We'll call the first the source, the latter the target. We could assume that there's some kind of bounded divergence between p of x and y and q of x and y. I'll call p source, q target. Or something like invariant conditional distribution. So if you're familiar with the covariate shift assumption, when people talk about covariate shift, sometimes people abuse the word covariate shift to just mean distribution shift. But actually covariate shift means that it is not an assumption of what changes, it's an assumption of what doesn't. Right? So covariate shift is basically saying there's sample selection bias over x. Like the marginal p of x is different from q of x, but that the conditional p of y given x is the same as q of y given x. It's the assumption that the labeling function hasn't changed. So it's this assumption right here. This, though, doesn't describe all cases of distribution shift. So in this talk, I'll talk about the reverse case. And basically, the covariate shift assumption, as I'll describe, corresponds to the assumption that x causes y. Dinner's ready. And when x doesn't cause y, except for in a degenerate case, p of y given x, like if y causes x, and there's distribution shift, then in general, p of y given x actually should change. And then you have a bunch of technology out here using sort of various deep learning approaches, often which are not specifying which assumption they're making. And we know that like what you assume about the world actually, but because these distribution shift problems are underdetermined, you have to make an assumption. And we have a lot of papers that are posing machinery without being clear about what assumption they're making. And yet some of it seems to have some interesting, like some of this deep domain adaptation stuff seems to do some interesting things, but sort of under unstated, implicit, or kind of murky assumptions. So this is, I'll kind of like do the indulgent thing of we're working through the technical papers in the order in which we wrote them. which is, I don't know, here. You like to think that like if you've done something right pedagogically, you've changed the order, right? It's like the order in which ideas occurred to you is not the order in which you should tell someone about them, but I haven't been able to find a better order, so we'll live with it. So here's a thought experiment that got me sort of thinking about just a little bit more deeply about distribution shift. So let's just say we have a quantification task. We would say, hey, it seems reasonable to say I have a machine learning classifier. It could predict a disease. I want to train the machine learning classifier, and then I want to use it in the wild, and I want to see use the classifier to try to detect if there's a change in the prevalence of the disease. All right, sounds like it makes sense. Sounds coherent. So I train. Let's just say like I've got access to the streams of like all the chest X-rays coming out of people's like routine exams, and I know which people were diagnosed with pneumonia, eventually at least or something, say within 30 days. And so what I'm going to do is I'm going to train a pneumonia predictor based on chest X-rays. So I'm going to go grab a ConvNet because it's 2019, let's say it's August. We train our pneumonia predictor based on chest X-rays. Pneumonia's not, that prevalent. So let's say I just made up a number. Let's just say it's 0.05% of the population. We're going to run our classifier on our training data because we trained a ConvNet. Our classifier is going to predict everything accurately, so it's going to say exactly 0.05% of people have pneumonia. Then we're going to say post hoc calibrate our classifier on validation data and find, of course, on on holdout data, now our model is going to predict 0.05% of the population to be positive for pneumonia. And we then go out and run it in the wild, the next day and find, indeed, the model's still predicting, if we were to just sort of average P of y given x over like all the images coming through the hospital, then we'd say that roughly 0.05% of people have pneumonia. And then an epidemic happens. It's January, suddenly, I don't think this would ever actually happen. If 5% of people had pneumonia, we'd probably pass some critical point where we're all going to die. I don't know. I'm not a pneumonia expert, but it seems a bit high. This is just a didactic example. So it predicts 5% of people have pneumonia. By the way, I don't think a patient has pneumonia. It's just what Google image search thinks epidemic looks like. I think that's an Ebola patient. So the question is, how many people really have pneumonia? So we train the model, and on holdout data, 0.05% of people had pneumonia. Now we run it in the wild. It says 5% of people had pneumonia. How many people have pneumonia?
Probably 0.05.
Do you think it's less than 5%? That's one thought. Any other ideas? Anyone think it's more than 5%?
It depends upon the data set that you have, right, or where you collected the data set from. If it is in Asian countries, then the pneumonia chance of the probability will be higher. And if it is more developed countries, it will be lesser.
Let's say it's in the same population in which we trained the original classifier. It's just at a different point in time.
Could go either way. Why would we favor lower than 5% more than 1%?
Well, that's the question.
It's unknowable. It could be just that they changed the scanning technology in January.
Right, so first of all, it is unknowable, right? It's underspecified. And the reason why is, let's just say all the images that are fed into the classifier are actually photos of cats. Then what is the classifier going to output? What's going to be the mean of p hat of y given x if all the images are cat photos? First of all, it's going to depend on the cat photos. But what do you think roughly you're going to see if you feed in all cats? Something between 0 and 1. Right, so it's hard to know. If you feed in cats and dogs into a classifier, and you train a classifier onto CFAR cats and CFAR dogs, train a ResNet, so you've got 5,000 cats, 5,000 dogs roughly, both in the training set, and then you take that classifier and feed in only horses. How do the horses get classified?
They get classified as cats or dogs with extremely high probability.
Stuff like that tends to happen. Most of the other 8 classes, most of the images get classified as cats. I believe more of them get classified as cats than cats get classified as cats. And if you feed in random vectors, like truly random, like just sampled uniformly in the box, then 100% of them are classified as cats. So it's like, who knows? Like I've trained a classifier on some support. I've fed in auto-support data. So it's, but the question is like, why are we even considering the possibility that we're looking at cats or that we're looking at data from a different country or that we're doing whatever? It's because we already know that we violated the IID assumption. We already know that our data does not come from the same distribution as that was used to train the classifier. That under which our sense of the classifier's performance is predicated, right? So given that we're willing to go there, then it's like, well, what have we assumed? So like, what is a reasonable assumption that we can make, and under which assumption, how does that affect our way of now kind of backing out to like what fraction of people actually have pneumonia? So another kind of motivation here for what I'm introduced in thinking about, so what I'm describing now is the label shift problem, and here's another motivation where we're not thinking about diagnostics, which is, let's just say we train a classifier to recognize objects, and we train with a uniform label distribution. Let's say we get 70% accuracy with balanced errors. So like our confusion matrix, the like column normalized confusion matrix looks like 70, 30, 30, 70, right? It's like the diagonals are all 0.7. And now if we deploy in the wild on any distribution of y, if all that's changed is the distribution of classes but not the class conditional distribution, then we're going to get 70% accuracy in the wild. So we're going to get 70% accuracy even if it turns out, say it's cats and dogs, even if it's like 100% cats, so the blind classifier would get 100% accuracy, we're still going to get 70% accuracy. And now we start to feel like we should be able to do better than that, right? Like you should be able to go out and say, okay, my classifier gets a confusion matrix of 70, 30, 30, 70. Now it tells me that there's 70% cats or whatever. I know that it would only tell me there's 70% cats if actually they were all cats. Maybe I should update my prior, maybe I should update my classifier, right? And indeed we do this all the time. We train classifiers on uniform label distributions. We tend to construct academic data sets in this way, and I'll even talk later about why that might even actually make sense. But then we just deploy the classifier in the wild, even though no real life distribution, in case of ImageNet, is going to have the same number of like axolotls and golden retrievers and the same number of mortarboards and motorcycles, and it's just these are the actual label distribution is very different. And could we actually get much better performance in a real world deployment setting without actually getting any new labeled data? And indeed, humans are able to do this. So actually, when I started working on this, I was like, humans must do this. Who do I know in psychology that hangs out at our conferences? And so I hit up everybody's favorite Twitter celebrity, Gary Marcus. we were in China for something. It was a weird time. It was a hysterical time in deep learning when students got, maybe it's still happening, right? It's like if you could train a ConvNet, you got a free trip around the world to speak at a conference you don't belong at. And I think it's like dying down just a little bit, the supply and demand is balanced. But anyway, so I hit up Gary and I said, do you know of any case, he talked about like human learning a bit, do you know anybody who's sort of demonstrating this kind of effect? And he just forwarded it to like NYU Psych Department, and someone came back to me with like the exact paper that and it should have actually been on my radar. I didn't even know they published kind of cog psych papers like this at ICML. It was actually an ICML paper for 2010, and they do precisely this. They show that people can kind of like update their priors and improve their predictions without any additional supervision, and they construct a sort of synthetic task where they have these like weird sort of objects, and I forget the exact details, but we can say that like they teach them some new categories of objects that they can classify kind of well but not perfectly. Let's call them like weebles and squeebles. So humans have some kind of error rate at classifying weebles versus squeebles, and they'll show every single person the same training set. But then what they'll do is at test time they'll change for different people. They'll show them test sets with different distributions of like weebles versus squeebles, and it turns out that basically the key finding is that you can induce someone to classify items differently by showing them a different like composition of the test set, right? So basically, if you show someone a test set, it's like if you ever took a standardized exam, like a multiple choice test, and you started going through and you're like, wait a minute, like like half the answers are C. And then maybe I should go back to that one that I guessed on. Maybe I should change the answer to C. And it's like your teacher might be like, that shows you didn't study and you have like a lack of confidence, but like maybe it shows that you're very serious about probabilistic inference and like you're just a rational person. But indeed, like maybe that's the rational thing to do. So here's the formal setup for domain adaptation. We have a source distribution P of X and Y, a target distribution Q of X and Y. We have these training examples, which are labeled examples that come from the source distribution. We have unlabeled test examples from the target. And our objective is to predict well on the test distribution without seeing any new labels. So in short, we want to, and more granularly, what we like to do is say, okay, first we want to detect that a shift has occurred. We want to estimate the new label distribution, and we want to correct our classifier sort of on the fly. We want to do this all without seeing new labels. And the relevant assumption that we're going to be working with, given our initial motivation, is we're going to say that okay, the joint distribution is changing, but we're going to assume that the class conditional distribution P of X given Y is fixed, right? So we can say it sort of corresponds to this generative model where we say that Y causes X. You don't have to assume a causal model, but it's the causal model that makes this particular invariance sensible, right? It's saying that you've intervened on X, you've intervened on Y, you've changed the marginal distribution of Y, but you haven't changed the process by which X takes its value given Y. So there are more cats or less cats relative to dogs, but what a cat looks like or what a dog looks like hasn't changed. Pneumonia has become more common or less common, but what pneumonia looks like or what not pneumonia looks like on an X-ray hasn't changed. So this is the anti-causal assumption, and I think it's important to, if you've thought about this already, it might be obvious. If you haven't, it actually might take a little bit of deprogramming, especially if you've never done any causal inference, because we actually, whenever we teach regression, we actually sort of pedagogically assume a causal model because we describe someone, assume generative process by which there's some background distribution over X, and then there's some structural equation by which Y's value is assigned given X and maybe some additive noise or something. We always describe it, this isn't really an equation, it's an assignment operation. And we always actually describe a generating process by which Y listens to X rather than that X listens to Y. But a lot of problems aren't like that, and diagnosis is one of them, right? The disease causes the symptoms, not vice versa. Although, I guess, if you get deep enough into it, what is a disease and what is a symptom is not always obvious, but this isn't a medical talk. Right. Bernard Shulkoff has a really nice paper that sort of laid out how covariate shift, label shift, and in various other kinds of concept drift map on to various assumptions about causal structure, and it's called uncausal and anti-causal learning from ICML 2012. So just to contrast this is different from covariate shift. Covariate shift, we say X causes Y. So basically what we're saying is it's P of Y given X that doesn't change. Thus we can factorize Q of X and Y, or Q of Y and X is Q of X times P of Y given X. Right? This is trivially obvious by the product rule if this were Q, but we're saying we can substitute back in P because because P of Y given X and Q of Y given X are equal. So it's, this sort of flows from the assumption that X causes Y. One of the reasons why covariate shift is sort of appealing in the context of domain adaptation is that we have samples of X from P of X, and we have samples of X from Q of X. So it's appealing that we would want to estimate the likelihood ratio of Q of X divided by P of X. If I were just a statistician and not the sort of machine learning clown that I am, I might not care. Why do I care about estimating quantities in terms of X or in terms of Y? But I am, a machine learner, and I am operating in a certain set of kind of data regimes. And the common one that I encounter is one where X is some horrible object, like an image or audio or a large text document, and Y is often something like a label. So something comparatively simple. So I don't want to estimate densities in terms of images because I don't think we have good machinery for that. But I'm much more comfortable estimating a density. And And moreover, all the machinery that we build, for example, if we're going to do two sample tests, we want to do it in the space that y lives in, not the space that x lives in, assuming we live in a world where y is low dimensional and x is high, because two sample tests become like multivariate two sample tests become like exponentially less powerful as like ambient dimension grows. Okay. So here's a simple procedure. We call it black box shift estimation. It's just sort of a moment matching estimator, where it's going to be a consistent estimator of the true test set label distribution. It's going to give us some intuitive error bounds. Its accuracy does not depend directly on the ambient dimension, so it doesn't matter how high dimensional x is, and we're going to get away with this because we're going to assume we just have a good classifier off the shelf, and we're going to use the classifier off the shelf to perform dimensionality reduction for us, and we're only going to concern ourselves with the outputs of the classifier. So we need a classifier off the shelf. It's going to be an adaptive method. Basically, if we have a better classifier, better by what criteria is a subtle detail I'll get to in a bit. But the better our classifier is, informally we could say like sort of the better our error bounds are going to be, and just the better our performance is going to be. However, we're not going to like make any really restrictive assumptions about our classifier. We're not going to assume that it's accurate. We're not going to assume that it's calibrated. We're not even going to assume that it's unbiased. And our estimator of the test set label distribution, or the target distribution label distribution, being consistent isn't going to rely on any of these special properties. So how are we doing on time? No? We got another hour?
Half an hour.
Half an hour, great. All right, cool. We're actually doing okay. So we're going to make the assumption that we already talked about, the label shift assumption. Class conditionals are the same. We're going to make sort of identifiability assumption here, which is just basically, hey, all the labels that we anticipate seeing at target time that have more than zero probability at target time have to be things that have more than zero probability at train time. Like, if you're going to show me images during train time of 10 classes, and then you're going to show me images at target time of 10 completely different classes, obviously I can't disambiguate them because I've never seen any of them before. Just like sort of just an obvious identifiability condition. We're just being formal here. The one kind of assumption that is maybe you haven't seen before, possibly, is just we're going to assume that the classifier that we have, the off-the-shelf black box classifier, it is going to have an expected confusion matrix whose that is invertible. Right? So it's just, all we're saying is that we have a confusion matrix of full rank. What we even mean by confusion matrix here is it can actually be quite liberal. It can be basically any function of our data, like any function that we can like split out by labels, that we just need to be like full column rank, where we have like one column per label, per actual label. But for now, it'll be easier to think about this as just say the hard thresholded predictions of your classifier, or the mean softmax output. So we can look at the expected confusion matrices, source and target time. And they're different objects from each other. So if we fix the classifier, and now we look at our source distribution, our target distribution, the expected confusion matrices are different. But they're only different because the columns are scaled differently, right? This is the actual y, this is the predicted y. If we fix an actual y, then we sample x given y, well, we're running it through the same function, right? So over here, like the distribution of f of x given y is going to be the same because the distribution of x of given y is the same in both distributions. The only thing that changes basically is the relative amount of mass on each of the columns, right? So if we column normalize our confusion matrix, now we've removed the degree of freedom, but now we have the column normalized confusion matrix is actually an object that is the same object on the source distribution and the target distribution. So this is important because we get the target distribution column normalized confusion matrix, and we can estimate it using data from the source distribution. Now, what do we do with our target data? So in order to calculate or estimate this guy, we need to be able to break out which data points, are samples from which column. For the target distribution, that data doesn't come with labels, so we can't separate out the columns. What we can do is we can just mush it all together. We can just take the mean. Right? We could say we could say the mean output of our classifier, our off-the-shelf classifier, evaluated on our samples that come from the target distribution, whose labels are unknown. And how are these objects related to each other?
Didn't you say before it was unknowable?
Well, what's unknowable is we make no assumptions. Here we've made the label shift assumption. So if we don't assume that we know that P of x given y is equal to Q of x given y, then we don't know what to do when we want to, say, estimate the target distribution label marginal. However, once we make the assumption that P of x given y is equal to Q of x given y, then the label distribution on the target actually becomes identifiable. And so that's what we've assumed here. The reason why this is the same on P and Q is because of this assumption. So this is the ingredient. It's that we have to make an assumption. We can't just look at our observational data and do a dance and talk about GANs, right? We have to. There has to be somewhere in there's a fundamental identifiability problem that we can't get away from. But once we make that assumption, then there's machinery that we could throw at it to actually estimate this. So how are these related to each other? These two objects? They actually form a linear system, and the solution to this linear system is the target label distribution, right? So the mean classifier output, because each column here is the mean classifier output when the label is y1, when the label is y2, when the label is y whatever, the mean classifier output, assume this is the actual expected confusion matrix, not what you calculate on samples. And let's say this is the actual expected classifier output on target distribution. So before we worry about estimation, just see how the actual underlying theoretical objects are related to each other. Right, this object is just basically like a mixture of these columns. And so we can just solve this linear system by inverting the confusion matrix, and we get our estimate. So we actually get back the actual target label distribution. The trick here now is to figure out the estimation error, because we're estimating this confusion matrix with finite samples. We're estimating this vector of the mean classifier output on the target distribution from finite samples. So right, we can solve it. If we solve this equation with the column normalized confusion matrix. What we get is an estimate of the target label distribution. If we just went back to our original matrix, which was just the regular confusion matrix where all the entries sum to 1, the only difference here is that this is now Q of y divided by P of y is the solution. So we call that our vector of importance weights, W. These would be the weights that we would use if we wanted to do, say, for example, importance sampling. So that's what we get. Consistency is relatively easy to show. We just need that the empirical confusion matrix converges to its expectation, which we get by law of large numbers, that the average classifier response converges to its expectation. It's also law of large numbers. And then we just need to show that the empirical confusion matrix is with high probability invertible as the number of data points gets large, assuming that the true underlying confusion matrix is invertible. And we can bound our error on recovering this vector of importance weights. And it's actually, I think, a pretty simple interpretable bound, which basically just says it depends on a few objects. One, this is a constant. This is the smallest eigenvalue of the confusion matrix. So basically, if our confusion matrix is degenerate, then recovery is impossible, and this guy is 0, and our error is bounded by infinity, right? This is going to be best if our classifier is perfect. For any non-zero number of the condition number of the confusion matrix, if the number n, the number of data points we use to estimate the confusion matrix, and m, the number of data points that we use to estimate the mean classifier output on target data, if these two approach infinity, then our error is going to go to 0. Also note here that we also depend on this term here, which is the vector of importance weights, the norm of the vector of importance weights. And so this is basically like a vector that's q of y1 divided by p of y1, q of y2 divided by p of y2, so on and so forth. So if q is unknown, and if q can be anything, and we get to choose p by like how we collect the data, then it's sort of, this is kind of makes sense as sort of if we want to minimize the worst case scenario over q for estimating the label distribution, and we have no idea what q is going to be, then we should pick p to be uniform. Right? As I said, we should do what we're doing. We should construct these uniform label distribution tests, at least if we can assume nothing about the label distribution in the wild. But the recipe is not to say, let's do that and then just deploy that classifier and hope for the best. It's to say, let's construct our data set in that way. And then, on the fly, as we collect new data, if we have a big body of data that's representative of the current label distribution in the wild, let's use that data together with our classifier that was trained on source data to estimate the current label distribution. Now let's take that label distribution, go back and sort of update our predictions on the fly to incorporate this new prior, so that you're always getting the benefit of incorporating the label distribution into making better predictions. If that makes sense. Right. So we can also use this sort of way of thinking for detection. Right. Like the one thing that this equation gives us is that, well, if this guy's full rank, then okay, this is a linear system, and we can use this linear system to solve for this guy. But we can also just think about this as specifying, well, if this is full rank and this is a linear system, then the mean classifier output changes if and only if, this is under the label shift assumption, the mean classifier output changes if and only if the label distribution actually changed. And so that means that it's sufficient if we want to detect shift, and we've made the label shift assumption, it's sufficient to restrict our attention to the classifier outputs. And so we don't have to worry about the high dimensional inputs. We can take all of our data, pre-process it by running it through our classifier, and now we have this comparatively low dimensional object for detecting distribution shift. We get to run our data through the classifier, and then we can do things like, depending on what we're doing, like if our classifier output is just is like the hard thresholded classifier, then I believe the provably like most powerful test that we have would be the likelihood ratio test or the chi-square test. If we are using our softmax outputs, then we have basically a k-dimensional, our classifier output is k-dimensional, where that's like the number of labels. We can perform something like a kernel 2 sample test over there, or KS tests on the individual components of the softmax output. Of course, then we have to like do some correction for multiple hypothesis testing, like the Bonferroni correction. So we have some empirical results. We show that when there is no shift, we control our type 1 error. The greater the shift, obviously, the more power of our test. Here, the greater the shift means we've created some sort of family of shifts whose like strength is determined, like how different they are from. So I'll just talk about the shifts we simulate in a minute. But you could just think of this as like how different from uniform the shift is. We also have, the better the classifier is, we tend to get better statistical power for detecting shift. For estimating the importance weights, you see that indeed, as we get more and more examples, we already know sort of analytically that we have a consistent estimate, but we just see it borne out. As we get more and more and more samples, our mean squared error for predicting the for estimating the vector of importance weights approaches 0. Now, what you see over here is the kernel mean matching approach, and basically what's happening here is that they sort of have some irreducible error by virtue of the fact that they have a kernel operating in input space over inputs. Conceivably, if they went to an infinite amount of data and shrunk the kernel bandwidth to 0, then like eventually, maybe you could get some kind of consistency result. But in practice, sort of performance that you're going to get with kernel mean matching seems to tap out here. And then what we did was we said, we can also improve our classifier. Now that we know the new, now that we have the new label distribution, we can go back, reweight our training examples so that they look more like the target data, right? So, and then we can retrain our classifier under the correct distribution and try to perform as well as possible. And indeed, we see that we do the same, our approach in unweighted when there is no distribution shift, and as the shift gets greater and greater and greater, spread emerges. Now, I realize at some point that this plot is very confusing to people who think about it for more than 30 seconds, because you say, hey, the shift is getting better, like the shift is getting worse and worse and worse. Why is the classifier getting better and better and better? And the reason why is because it's becoming an easier problem. Because we're working on CFAR data, which the original distribution is uniform over the labels, so it's actually hard. Like the blind classifier here gets performance of 10%, right? And as you move to the right, we're simulating, we'll tweak one shift, we're just saying that we've picked one label, and this one label's prevalence is getting greater and greater and greater and greater, and the others are, still uniform amongst each other. But so basically, at the extreme side, one label dominates, and we've done this for every choice of the label, and plotted the spread. Here, in what we call Dirichlet shift, we simulate the label shift by basically sampling the target label distribution from a Dirichlet with a concentration parameter alpha, and then we do this many times. And so basically, the smaller the concentration parameter, the more the mass. Over here at like 0.001, it's basically one label just dominates always. For smaller values of alpha. For larger values of alpha, the distribution becomes more uniform. So here what we've done is imported importance-weighted empirical risk minimization. And God is telling me that my battery is running low. This horrible thing happens in New York where the rats swirl around the city and their tails become tangled up together until they become one giant organism. And the same thing happens in my backpack, but it's with power cables. So overall, this work, we kind of wanted to take a step back in the next paper, which was actually just presented, 3 days ago or something, by my visiting student, Stefan Rabanser, who is applying to PhDs. The idea here was to say, let's take a step back and say, okay, we've proposed a sort of general pipeline which says, hey, the way we're going to detect shift is we're going to do dimensionality reduction first, and then we want to we're finding a representation where we hope that in that representation we're able to sort of efficiently recognize distribution shift, do efficient two-sample tests. And is there anything special actually about the representation that we've come up with? So we look at a number of different dimensionality reduction methods. We look at no dimensionality reduction because I believe in baselines. So just doing KS tests on the individual pixel values. We look at PCA, we look at sparse random projections, we look at untrained autoencoders, trained autoencoders. Doing this black box shift detection method where basically our relevant representation is the output, the softmax outputs of a classifier that was just trained on some partition of the source data to predict a label. Same thing, but the hard thresholded version. And then we look at the classifier approach, right? Which is, I think, if you're a machine learning person and not a stats person, then like the classifier approach might be the natural way that you think about trying to detect distribution shifts. You say, I'm going to try to train a classifier to like a domain discriminative classifier to distinguish between the source and the target data, right? And the question is, you know, is there something special about what we came up with? So in this case, right, like if you did this and you created a balanced sort, train, and test set, basically if this got any better or worse, like statistically significantly than 0.5 accuracy, then you could be confident that, you know, you had detected some distribution shift, right? Because if there were no distribution shift, it should be impossible to distinguish between the two. And we look at all kinds of different shifts. We also want to see, well, you know, okay, we've created this machinery, but then what happens when we violate the label shift assumption? So we look at, you know, label shifts, but also various combinations of label shift, noise, rotations, or whatever. And you say, well, our method is only guaranteed to detect shift under the label shift assumption, which is that the only thing that changes is the label distribution, right? Now, if the class conditional distributions are also allowed to change, our method is not guaranteed to detect shift, and in fact, I can easily construct a distribution that would be like, it would be invisible to like to this detection method, right? There would be shift that our classifier couldn't pick up, and the way you could do that, right, is you just find, you have high dimensional input, low dimensional output from your classifier. Just go out and find different inputs that map onto the same output, because they have to exist, and just shift the mass among them, right? But that's only like an adversarial construction. You think if you're in anything but an adversarial setting, it's like you have some distribution of classifier outputs. Then if you have label shift, your distribution of classifier outputs is guaranteed to change. Then what are the odds, like if that then, you know, you change a class conditional distributions, that you're going to move the distribution of classifier outputs exactly back to what they were before? And the answer is like that's like a zero measure subset of possible distribution shifts. One that determined adversary might be able to like work out, but not necessarily one that could ever happen naturally. So the short story is that across many different settings, and this is a kind of very like meta, like I'm going to take this too seriously because this is averaging over many different experimental settings. So it's not like with reference to a particular underlying distribution that we're calculating accuracy. It seems across all of them, across the majority of them, that actually this method of using the classifier outputs as our representation for detecting distribution shifts seems to be the most effective. We could see in cases where there is actual shift, what is and there are subtle issues here of like multiple hypothesis testing that need to be talked about offline or at greater length. But like basically the idea is to just kind of get a sense of at roughly what number of samples does each of the different representations, you know, how many samples are required within each of the different representations before like the two sample test will identify yes, there's a shift. And we find across many different settings we do better with this classifier output. You know, I think like looking at the classifier itself, the domain discriminative approach, it seems to you know, not do very well with a small number of examples because we're looking at something like image data, and in order to do anything at all, it needs to learn a representation, right? Now, I think there's maybe subtle ways you could try to improve this by having like pre-trained representations for the domain discriminative one that actually come from the label classifier and then fine-tuning it or whatever, but we didn't do that here. And obviously, we also look at varying what fraction of, if we apply a perturbation, it's like to what fraction of samples. One interesting thing that comes up, and again, this is something that I think once you know it, you could probably design an adversarial attack that will fool it. But when we look at adversarial data, and let's just focus over here where 100% of the data are adversarial attacks on the classifier, one weird thing that pops out is that actually, by far, the best method for detecting the adversarial attack is the no reduction. It's just looking at the raw pixel values. And so the weird thing here is that these examples, these adversarial examples, look exactly or imperceptibly different from the original ones to us. But if you were to just look at the CDF for for individual pixels, without even combining. We just say, there exist pixels among where the CDF on that individual pixel is so different that just by looking at a single pixel, you can say, oh, these are not from the same distribution. But like, that is just not how we parse images. You wouldn't say like, oh, pixel 9 down, 14 across, like definitely differently distributed on this data set than the other. What I haven't looked at is like, how you would design an adversarial attack that can preserve the per pixel marginals while still fooling a classifier. But that was something interesting to see, that they're like really easy to detect, actually based on the raw distribution. We also got to apply some of our machinery to show there was this question. I don't know if you saw this paper from Ben Recht about like how well do CFAR classifiers generalize to CFAR, how well do ImageNet classifiers generalize to ImageNet, and there was some degradation in performance, but the sort of ranking among the models actually was the same as like what we think the ranking of the model is based on our like smashing the hell out of the test sets on these problems. And the question is, well, to the extent that the classifier performance fell, is that actually because we've been overfitting the test set, or is it actually because despite their best efforts, there is distribution shift? And so we used our machinery, we were able to show, on first try that indeed there is a significant distribution shift between CFAR 10 and Ludwig Schmidt 10. Ludwig is also on the job market this year, so So I just want to touch on a couple other things. So when we corrected for distribution shift, we used importance weighting. And there's a question of like, this sort of seems natural. Like it's sort of our go-to. Like there's distribution shift, there's shared support. Let's reweight our training examples so they look like our target examples and retrain. And the motivation for importance weighted, so importance sampling is used all the time to estimate various quantities, but in the context of importance weighted risk minimization, in like the original papers, it's like Shimodaira and like statistics in like 2000, the motivation comes from model misspecification. Right? It's clear that it makes sense if you're trying to fit a linear model and your real pattern is something that's a little bit more like this quadratic. If your data comes from, the domain of X is from, negative 0.5 to 1.5, then you're going to try to maybe fit this black line. But if it turns out that, at target time, you're only going to see data from here, you're going to fit this other line, right? And it's basically because your classifier is high bias, incapable of fitting the whole distribution. If you change the set of data points, or you can change the range of X that you're looking at, you're going to come up with a different model. But the question is, deep neural networks trained on image data are usually trained to shatter the training set. And in that context, when the models are over-parameterized and they're actually fully separating the data, what, if anything, is the impact of importance weighting on the models? And so I got really worried because we've been doing this, a lot of people are doing it, and I'm not a theorist, but I'm an ally. And so I was at a talk in Haifa at the Technion, and Nati Cerebro was giving a talk about his work, trying to understand what's going on in these over-parameterized models. And because he's a theorist, he starts with, okay, let's talk about linear models. So the simplest neural networks, linear models, binary classification, optimized by gradient descent. Eventually they extended the results to stochastic gradient descent and deep linear networks and convolutional linear networks. But for now, let's say gradient descent on linear networks with linearly separable data. So, and when you turns out, if you train a model by gradient descent on linearly separable data with log loss, what do you converge to? What do the weights converge to?
Infinity.
Oh, right, so the weights converge to infinity because there's no finite minimizer of the loss. So the weight norm goes to infinity. So the weights don't converge to anything. But what do the weights converge to in direction? So W divided by the norm of W does converge.
Max margin.
Max margin, exactly. So it turns out that what happens is you optimize the loss, like log loss, and the weights start blowing up in norm. As the weights blow up in norm, the support vectors start dominating the loss, and so they start determining the location of the decision boundary. What bothered me about this is says, okay, here's a single neural network, where optimizing log loss like we are with a particular architecture, but that basically says importance weights for this simple neural network have no effect. Like if I'm training to separate the data, it doesn't matter if I triple sample the purple points. My decision boundary will show up in the exact same place. Right? And so what kind of worried me is sort of like, what's going on here? because we think we have these results that we reported in a paper saying we're doing importance weighting and deep neural networks, and we're getting these good results. But on the other hand, our problem's better motivated using crappy models, so we weren't fully separating the data, and we also weren't training it forever. We weren't leaderboard chasing. And so I went back and sort of thought, is this true for like in general for deep networks, or is at least true for deep networks to separate the data? And if so, what does this say for like the general practice of using importance weighting in the context of these sort of like data shattering deep learning problems? And so we show, okay, first of all, we can just see even on the two-dimensional binary classification problem, indeed, this happens. It's a very slow convergence, right? So this is, on 2D data, we're still seeing convergence between like epoch, 1,000 and 10,000. But indeed, we, whether it's 1 to 10 or 10 to 1 importance weighting, we see a big difference here where a much bigger volume after one epoch is classified as green, a much bigger volume here is classified as blue. The red line here is logistic regression. The coloring is multi-layer perceptron. But indeed, like after 10,000 epochs, you can't distinguish based on the decision boundary whether you had importance weighting of 10 to 1 or 1 to 10. So we do this, and we talk about classifying cats versus dogs. So we classify cats versus dogs, and we look to see for very different settings of the importance weights what happens. And indeed, it seems as we train for more and more and more epochs, the fraction of holdout images classified as cats versus dogs converges to more or less the same thing. Like something kind of weird and unstable happens when you go to importance weights of 512. But up until then, importance weights of 120, this is a classifier that gets 80% accuracy. So the classifier is getting 80% accuracy, and I go to the classifier and say, actually, I'm telling you now, at test time, 99.5% of images are going to be dogs. You'd like to think that classifier is going to start classifying, way more dogs. But it doesn't classify a different fraction of holdout images as dogs. This is showing what happens when you classify images from the other 8 CFAR classes. You can see they're all a little bit cat-like. And you can see here, as we vary the importance weights, basically within this like stable range, like 128 and 128 in the other direction, we don't have an appreciable difference in the fraction of holdout images classified as dogs, either among dogs, among cats, among images from the other classes, or even like among random vectors, 100% of which are usually cats. L2 regularization seems to have some small effect, but the weird thing here is that now what we've done is we've taken this tool that we have for expressing our importance weights, and we have this correction that now, to the extent to which this correction is applied or not, or has any effect, is now expressed in terms of the early stopping criteria and the L2 regularization, which seem to be like conceptually the wrong knobs to be turning, right? Like what is the right epoch to stop on to achieve the correct effect of the importance weighting? And it's like really severe, right? Like you look at this here. If I stop on epoch 400, I get one answer. If I stop on epoch 402, I get a completely different model out. So what should we be doing? Should we be doing importance weighted risk minimization at all? There is an alternative here, right? We could post hoc calibrate our probabilities, and then we could actually just apply an analytic correction where we would reweight our predictive distribution by the likelihood ratios. So what I'll close on, if I can, is there's a lot of work now that is based on a kind of intuition that says, hey, what we should do is something GAN-like. And say, let's, the way we're going to do, and so first of all, the statement is sort of like, we're going to make no formal statements about how the source and target distributions are related to each other. We're not even going to assume they have shared support, because they're addressing problems like, street view house numbers and MNIST, which really don't. There's 0 black and white images in one. There's 0 natural images in the other. And say, well, here's what we're going to do. We're going to learn some kind of encoder such that in the representation that we learn, the source and target data are indistinguishable from each other. We'll say if they're in some sense, we want to think that we somehow align them in latent space, and then so that the source data is classified correctly, but the source and target data are indistinguishable from each other. And this sounds like a nice idea, and indeed sometimes seems to empirically get some nice results. And they even claim to have a theorem from 2010 that says they're doing the right thing. And this theorem is the result of work by Scheib and David, and it says, hey, the target error is bounded by a sum of 3 terms. It says it's bounded by your source error plus some divergence between the representations of the source and target data, plus this term, which has to do with the divergence of the labeling functions applied on top of those representations. And what these guys say is sort of basically, let's just ignore the 3rd term, and let's minimize the first 2. Right? So the adversary is minimizing this one and saying the representation should look the same, and the classifier loss is minimizing the first one. The problem is that minimizing this sum of 3 terms is not a necessary thing to do. It is a sufficient thing to do. And in fact, sometimes it's the wrong thing to do, because by this term, like if these 3 terms are all 0, this is guaranteed to be 0. But sometimes actually, by minimizing this term, you maximize the 3rd term, and the 3rd term is the killer. The 3rd term, like as long as your source error is 0, having the applicable label on the source and target data be divergent basically is like lower bounding your error on the target data. So you're basically, by virtue of making your data look the same, you're making your error blow up. And so when is like the failure case? So this is the thing I think you should be able to look at for like a minute and sort of see like something's wrong here. And the easy case to see when it's wrong is when the label shift, when the label distribution shifts. They don't have to be in the label shift assumption, just when the labeled distributions shift. So the only way, if I have way more positive points and negative points in target data, and they're balanced in source data, the only way I can make them look the same in representation space is if I siphon off some of these positive data points and I make them align with source negative data points in representation space. So you shouldn't make them look the same. But again, domain adaptation is in general impossible. It's the kind of problem that needs to sort of like be treated with a certain kind of respect, and you have to be clear about what assumptions you're making. So they and you don't get away with things the way you do in supervised learning, because supervised learning, the relevant sort of sample size that you're encountering is the number of samples you have. In domain adaptation, in some ways, the effective sample size for the kinds of claims you want to make is the number of shifts you've seen. And each shift is a whole data set. And so what's happened is they've worked only with academic data sets where they all happen to have uniform label distributions. And it seems that what they're doing, for some heuristic reason that we don't understand, works in 1 or 2 data sets. But actually, if the label distribution is different, things go kind of horribly wrong. So we came up with some fix to the method that, to be constructive, it's not guaranteed to work, but it's not guaranteed to fail, and empirically works better. Specifically in the case of label shift. And what I'm really excited about now is some work related to using humans in the loop to intervene on data and actually give us some sense of the causal structure in it, but I don't really have time for this part, so I guess I'll have to write a blog post or something. Anyway, we did like 90%. Call it success. Anyway, thanks for having me.
Slightly over time, and I don't want to cut into lunch, so we'll take only the most enthusiastic question. Go.
It's like that classic talk show. It's like I'm the last thing standing between you and dinner.
That was a lot of information. Thank you, nice presentation. So if I summarize it, initially you said that label distribution should be, we were looking for equal label distribution initially. Then you suggested that that's not the right way. That's how you ended it, right? In the end, you concluded that label distribution needn't be equal, or it will be in different form in reality.
Right. Well, we don't get to choose what the distribution is, right? We don't get to choose nature. We just get to just figure out if there's something, if there's some structure in it that allows us to make the right decision.
True.
What we can't do is naively assume that something like the label marginal is going to be the same in source and target data when there's no reason to believe it will be. Then to only test on data sets where that condition holds, and then sort of apply in a wild where in general that won't hold, and then it's not like technology that breaks horribly.
So initially you mentioned about Bird 2 being adversely attacked, right? But say now Google deployed in their search engine, it's not like somebody can attack their model because it's inside a system, right? Because some kind of system integration will be done, like hardware. Probably a determined person or a determined entity or government can attack it, but because it's inside some system level, it's very difficult to do an adversarial attack, at least in that, with respect to if you're deploying NLP models in search engines.
I don't know if that's true. The one thing I like about the spelling attacks is that with vision attacks, like I don't know of any self-driving cars that actually work, let alone of people attacking them with like adversarial stop signs. But the case of fooling sort of various sort of like AI systems by perturbing text adversarial has been going on since the dawn of email, right? Like this is the spammer's toolkit. Is you want to doctor the spelling of certain words, whatever, to evade initially rules, right? Like blacklists of like words that are sort of predictive of spam, and you try to say, oh, this isn't Lipitor, this is lip with 2 P's, ator, and then you could try to sell black market drugs to people. And those are spam filters. They are part of a software system, but the spammers they don't get white box access, but they get black box access. They get to sort of try modifications and see what comes out and update their strategies.
Okay, so it's going to be lunch now, and I'll let over lunch you can ask Zach why P of X given Y equals Q of X given Y is a reasonable assumption.